You're kneeling in the dirt. Your hands are raw. You've been hauling cut stone since dawn, and your shoulders burn with a weight that has no name. You won't set a record today. You won't win a medal. But your bones are building walls inside themselves that no modern athlete will ever match. Let's turn the page. Because what happened inside the skeletons of people like you, people who worked, walked, carried, and dug for a living, is one of the most startling findings in the study of human strength. And it has nothing to do with the gym. The obvious place to start is load. How much weight did your body move in a day? Not in a single lift, not in a set of 10. Across the full arc of sunrise to sunset, how much mass traveled how far because of you? Researchers who lived with foraging groups in southern Africa tracked this. Women and men carried bundles of tubers, firewood, game, and water across open ground day after day. The loads were heavy and the distances were long, repeated and varied across ground that was never flat, never paved, never the same. Now picture the other side. A modern Olympic lifter steps onto the platform. The barbell bends under enormous weight. The crowd roars. In a single session, that lifter may move far more total weight, but the barbell goes up and comes back down. The feet don't travel. The hips don't swing through uneven ground. The torso doesn't twist to dodge a branch or step over a root. That lifter's total distance is zero. This is the gap that changes everything. It's not about who is stronger in a single moment. It's about what the skeleton learns from a lifetime of movement. And bones, it turns out, are very good students. But what does a bone actually learn? To answer that, you'd need to slice one open. Not along its length, across it, like cutting through a pipe. What you'd see is not a solid rod. It's a ring of dense material wrapped around a hollow core. The thickness of that ring, the way mass is spread around the center, the overall size of the cross-section, these tell you how much bending, twisting, and crushing that bone can take. Think of it like a bridge beam. Engineers don't just make beams heavier to make them stronger. They spread the material outward, away from the center, so the beam resists bending in every direction. Bones do the same thing. And the body of a late Stone Age hunter did it better than almost anyone alive today. Their thigh bones had dense outer rings far larger than what you'd find in an elite power athlete. The difference wasn't small. It was roughly a third more resistant to bending. That's not a quirk of genetics. That's a skeleton that spent decades responding to loads from every angle. Walking uphill with a deer carcass on your shoulders doesn't load the bone the same way as walking downhill with a basket of roots on your head. Digging with a stick twists the leg differently than sprinting after prey. The bone never adapted to one motion. It adapted to all of them. But here's where it gets strange. You might expect that the wall of the bone, the dense outer shell, would be thickest in people who lifted the heaviest single loads. That's the gut feeling. Heavier weight, thicker walls. And it's wrong. Researchers measured this shell in the thigh bones of people who worked ancient stone quarries. These weren't athletes. They were laborers who chipped, hauled, and dragged stone for years. Their bone walls were about a quarter thicker than those of modern Olympic lifters. People who train with some of the heaviest loads on Earth. The gap runs in the wrong direction from what most people would guess. The quarry workers didn't lift more in a single effort. They lifted less, but they did it for hours across miles through seasons. The bone responded not to the peak of the load, but to the rhythm of it. Moderate strain, applied again and again, in patterns that shifted with the task, triggered the outer surface to keep adding new layers, like a castle wall that grows a new ring of stone after every siege. Except the sieges came daily and the wall never stopped growing. So bones are thicker. They're wider. They resist bending and twisting better. But what about the places where muscles actually grab on? Because a bone isn't just a passive column, it's an anchor point. Every major muscle in your body attaches to bone through a rugged patch of tissue, a ridge, a bump, a rough surface where tendon meets mineral. And these anchor sites tell their own story. You're standing in a cave in what is now France. It's roughly 40,000 years ago. The person beside you has just thrown a spear at a bison. Their shoulder rolls forward. The tendon of their main shoulder muscle yanks hard against the upper arm bone. Over years of throwing, carrying, and pulling, that bone builds a ridge at the anchor point. The ridge grows wider, rougher, more textured, like the roots of a tree gripping deeper into soil with every storm. When scientists measured these ridges in Upper Stone Age people, they found surfaces vastly larger than the same spots on modern competitive rowers. The link between ridge size and muscle force is direct. More surface means the muscle can hold more force. The ancient shoulder wasn't just bigger, it was built to handle more power, not because of bulk, but because the anchor itself could grip harder. Would you have guessed that a person who never touched a barbell could outpull a trained rower? That's the twist. And it points to something deeper than exercise science. Let's turn the page again, because load alone doesn't explain the full picture. Bones don't just respond to force. They respond to the chemical world around them. And for most of human history, that world shifted with the seasons. Winter meant different food. In cold climates, winter diets leaned heavily on animal fat and protein. Summer brought plants, tubers, fruits. The body swung between surplus and scarcity, between dense calories and lean ones. And those swings left marks. Bone density didn't stay flat across the year. It rose and fell with the diet, climbing during seasons of high animal intake and dipping when food was scarce. The body treated each surplus like a building season, and each lean stretch like a rest phase. Over decades, these cycles stacked. Layer on layer, season after season, the bone grew denser and thicker than it would have under a steady, unchanging diet. But even that isn't the deepest layer, because the body doesn't just build bone in the moment. It writes notes for the future. This is where the story gets quiet and a little eerie. Inside every bone cell, your DNA is wrapped around tiny spool-like proteins. Chemical tags sit on the surface of that DNA, small molecules that act like dimmer switches, turning genes up or down. When a bone cell feels repeated strain, some of those switches shift. Genes that promote bone growth get turned up. Genes that slow it down get muted. Researchers found this in competitive rowers. After a full year of heavy training, a key growth gene in their bone cells had its dimmer switch turned clearly toward one dot. Density climbed. Thickness grew. The strain had left a molecular memory, a setting that pushed the cell toward building more bone in the future, even before the next load arrived. Now here's the question no one has fully answered yet. How long does that memory last? Does it fade when the training stops? Does it pass to the next generation? Some evidence suggests these marks can persist, that a parent's physical life may bias their child's bone cells before birth. But this is contested ground. The data is young. The debate is live. And anyone who tells you the answer is settled is selling something. What we do know is this. The mix of varied load, seasonal nutrition, and molecular memory created a system that modern training rarely copies. Gyms are designed for control. Same movements, same angles, same rest periods, same meals. That control is useful for safety and for tracking progress. But it strips away the very chaos that built the strongest bones in human history. Now, someone watching this might push back. They might say that modern training is smarter. Planned programs, precise nutrition, recovery science. These tools let athletes target bone growth with pinpoint aim. Why would anyone trade that for the messy, dangerous grind of hauling stone across a hillside? And that's a fair challenge. Peak loads in a gym do trigger bone growth at specific sites. The science is clear on that. But here's the limit. A barbell moves in one plane. A squat loads the spine and hips in a straight line. A deadlift does the same. The bone adapts to resist force along that line and becomes strong in that direction. Take the same bone and twist it, bend it sideways, load it while the body is off balance and moving over rough ground, and the gym-trained bone doesn't perform the same way. The ancient bone does, because it was never trained in one direction. It was forged in all of them. There's another wrinkle worth pausing on. Not all ancient groups had equally strong bones. A herder who walked high mountain passes with livestock built different patterns than a farmer who tilled flat river plains. Coastal groups who paddled, dove, and hauled nets showed arm bones shaped for pulling, while inland hunters showed leg bones built for sprinting and carrying. The romantic idea of a single-orn ancestral strength is a myth. What's real is that every group adapted to its own blend of tasks, and nearly all of those blends produced more varied loading than any modern sport. Even among women, the pattern holds. This matters because a common belief is that female skeletons are simply smaller and weaker by default. But when you compare foraging women to modern female athletes, the foragers match or beat them in bone wall thickness and cross-sectional size. The gap between ancient women and modern women is far larger than the gap between men and women in ancient groups. The difference isn't sex, it's workload. So where does this leave us? Not with a command to abandon gyms and start hauling rocks, but with a question that won't go away. What if the strongest skeleton isn't the one that lifts the most in a single moment, but the one that carries, walks, twists, digs, and climbs across a full life? What if variety is the load the bone is really waiting for? If this story changed how you think about strength, you'll want to hear what we found about the diets that built the strongest hearts in human history. That one's waiting for you right now. And somewhere beneath your skin, the same bone your ancestors carried across open ground is still listening, still waiting for a signal it was built to receive. The question is whether you'll ever send it.